Okay, so here's a scenario. To make money, the school has decided to turn the maths room into a giant ball pit. Unfortunately, we have to comply with a number of regulations, so there has to be at least one adult for every 3 children. There are no more than 12 children to be allowed in the room at one time, no more than 8 adults at one time, and no more than 18 people in total, adults or children. So under those restrictions or constraints, we're going to charge 60 krona for each adult, 50 for each child, and we want to make as much money as possible. So let's start thinking about formulating this mathematically. Let's say there are X adults and Y children. So our first constraint is that there must be at least one adult supervising for every 3 children. So if Y is the number of children, there have to be more than 3 adults per children. So number of children divided by 3, Y divided by 3. The number of adults has to be more than that. So X is greater than or equal to Y divided by 3. I can multiply both sides of that by 3 to make it a bit tidier, and say 3x is greater than or equal to a whole y. And then I can just flip that around and say y is less than or equal to 3x. So I've just changed the order of that and written the y first, less than the 3x. The reason I've done that is so that it looks more like the general formula for a straight line that we're used to, because we're going to start plotting this as lines and regions on graphs. Okay, the next one. No more than 12 children are allowed to be in the room at one time. So the children is y, so what we're saying there is that y has to be less than or equal to 12. No more than 8 adults at one time, so the adults are x, so we're saying x has to be less than or equal to 8. And then no more than 18 people in total. So the people are the adults plus the children. So we're saying x plus y has to be less than or equal to 18. So those are our constraints. And then our profit is going to be 60 krona for each adult and 50 krona for each child. So we're trying to maximize our profit of 60 times x plus 50 times y. 60 krona for each adult, 50 krona for each child. So taking those constraints, we can start plotting those as lines on graphs. So starting with the first one, y has got to be less than or equal to 3x. So I've put the x for the adults on the horizontal axis and the y for the children on the vertical axis. So we know how to draw the line of y equals 3x. So everywhere on the line y is equal to 3x, but we want the region where y is less than 3x. So what I'm doing here now is shading off the region I don't want. So anywhere above the line, y is more than that. So I'm only interested in the area below the line where y is less than 3x. Now I'm looking at the inequality that says y less than or equal to 12. Well, the horizontal line at 12 represents everywhere where y is equal to 12. So anywhere along this line, y is equal to 12. But we want y to be less than or equal to 12. So we're only interested in the region underneath that line. So I've shaded off everything above the line, and I'm only interested in anything under the line. Our next constraint says that x has to be less than or equal to 8. So there's the x-axis there. 8 is there. So anywhere on that line, x is equal to 8. But we want x to be less than or equal to 8, so we're not interested in anything to the right of the line. So shading all that off, we're left with this bit here. And then we've got x plus y is less than or equal to 18. So we want to draw the line of x plus y equal to 18, and then shade one side of it for the bit that we don't want. Okay, so the line of x plus y is equal to 18. We could rearrange that as y equals something x plus something on the end by multiplying, dividing, adding, subtracting things to both sides. But another way to approach these things, where it's x and y on one side equal to something on the other side, is to think about what if x or y was 0? So if x was 0, then you just have y and 18 on either side. And if y was 0, you just have x and 18 on the other side. So you know that the line of x plus y equals 18 is going to go through 18 on both axes, because you know that when x is 0, y is 18, and you know when y is 0, x is 18. So that's another way to plot lines like that, where you have the x and the y given to you on the same side of the equation. There are other ways to do that. But we're only interested in the bit underneath the line where it's less than 18. So I'm going to shade away everything above the line, and then I'm left with that bit there. Now there's one more constraint that hasn't been mentioned here, and that's that x and y both have to be more than 0. So I'm just shading everything underneath the 0, because you can't have a negative number of children or adults. So that leaves you with this bit in the middle that we haven't shaded. So that unshaded bit represents anything that satisfies all of our constraints, and that's called the feasible region. So it's where all the possible, allowable solutions are. And the key bit of theory to this is that the profit, or I'm going to use some terminology now, objective function, that objective function, our profit function in this case, is optimized somewhere at one of the vertices on the feasible region. So a vertex, remember, is a corner of a shape with straight edges. So at this point, for example, we've got x equals 4 and y equals 12. And if you plug that into the objective function, that gives you a profit of 840. So 4 adults and 12 children gives you 240 plus 600 kroner, 840 kroner. Now we're going to consider another point on the another vertex of the feasible region over here. Now over here you've got 6 adults and 12 children, and 6 adults plus 12 children gives you 960 kroner when you plug 6 and 12 into the profit function. 960. Now we're going to think about this one, and that gives you 8 adults and 10 children for a profit of 980 kroner. Down here you get 8 adults and no children for a profit of 480, or down here, no adults and no children for a profit of nothing. So in fact, our optimal solutions and our worst solution are all vertices on the feasible region. So the best one was up here with a profit of 980. So the most money you can make is 980 kroner from 8 adults and 10 children. But the key piece of theory was that, going back, that the optimal value of the objective function is a vertex of the feasible region. So optimal value just means the best value. The objective function is the thing we're trying to maximize. So this equation for profit, 60x plus 50y in this case, that's 60 kroner for each adult, 50 kroner for each child. Vertex means just a corner, there or there or there or there or there. And the feasible region is the bit we're left with after we've shaded away all of the things that were not allowed because they don't satisfy the constraints. This whole topic is called linear programming.